Hello everyone. I would like to present our work, Dynamic Public Resource Allocation based on Human Mobility Prediction. This is Sijie from Xidian University in China. Public resources such as billboards, trash bins, and surveillance cameras are deployed by companies or governments for different purposes. The goal of the allocation of those resources can be roughly summarized as covering as many people as possible with limited resources, which has been extensively studied in previous years. However, due to the nature of human mobility, the crowd distribution is highly uneven on both spatial and temporal domains. As a result, redundant resources have to be deployed to guarantee the desired crowd coverage. The figure shows the spatial distribution of trash bins as well as crowds over a day at Happy Valley, a popular theme park in Beijing. It is clear that the trash bins marked with rectangles are not always in service. The right figure shows the utilization of 95 trash bins during the whole day, where 70 to 80 trash bins are not fully utilized. Apart from non-data-driven static deployments, the dynamic of crowd flows is also another important factor leading to such low utilization. Based on these observations, a natural question arises. Is it possible to serve more people with fewer resources if those resources are mobile? Fortunately, with the rapid development of robotic systems, various unmanned vehicles emerge for logistics or transportation purposes. Furthermore, some companies like JD.com are developing the common mobile bases that can carry any payload, which can make resources mobile. However, it is still a non-trivial task to design effective scheduling for these dynamic public resources or mobile agents. The first reason is that our resources are limited due to budget constraints, so that we cannot cover all area at all times. The second reason is that the mobile agents have energy constraints. If we always move to the maximal coverage locations of each time step, the energy would be used up easily. The third reason is that the action space is large. A mobile agent can move to any location in a region, and that location can also be served by any agent. Computing an optimal solution is extremely time-consuming. To overcome the first two challenges, we first perform a multi-step crowd-flow prediction so that we can have a better understanding of future dynamics of crowd-flow distribution. Then we propose the multi-agent long-term maximal coverage scheduling problem, which schedules multiple mobile agents based on the prediction results to collaboratively maximize the crowd coverage during the service time of a day, while considering the energy limitation of each agent. To further tackle the third challenge, we propose a heuristic algorithm, energy adaptive scheduling, to schedule mobile agents efficiently and effectively. In our problem setting, the service area is discretized into uniform grid locations, and each grid location has a crowd flows reading dynamically changing with respect to time. We also have k homogeneous agents, each of which has the same energy limitation. Each agent has a service radius, which indicates the size of coverage area in its neighborhoods. The crowd flows in a grid location are covered if there is at least one agent can serve the grids. There is a static charge station in the region, and all agents must start and terminate their trips at the station. Then the problem is defined as follows. Based on the predicted crowd flows until the end of the service time, which can be obtained using existing methods, we calculate the visiting location sequence of agents so that the daily crowd coverage is maximized without using up the energy of each individual agent. Knowing the long-term prediction will never be accurate enough, we apply the model predictive control strategy. There will be several decision times during the service time. When a decision time arrives, based on the real-time observed crowd flows, the future crowd flows are predicted. Then the problem would be solved again based on the most fresh crowd flow predictions and the current location and the remaining energy of each agent. And only the first future location assignments of each agent is actually used. Given the NP hardness of the problem, we propose a two-step heuristic algorithm, energy adaptive scheduling, to solve it efficiently. The first step is multi-level max cover scheduling, which tries to find a schedule to visit the maximal K coverage locations at each step, so that the energy of each agent will not be used up. If a such schedule cannot be found, we execute the second step, energy-aware scheduling. The main idea is that we first initialize a policy that agents are sent to the locations that maximize the coverage of average future crowd flows and fix at those locations in the future. Then a hill climbing based algorithm is applied to improve the current policy. We evaluate our proposed method on real-world graded crowd flow datasets in Beijing Happy Valley. We also collect the locations of trash bins in the park by on-field investigations. We calculate the number of resources required of different methods to meet the same average daily crowd coverage of the current deployments. EADS achieves 80% and 56.8% resource reduction with respect to the current and the static maximal coverage deployment strategies, respectively. Thanks for your attention. Our data and codes are publicly available.